Okay, and welcome to Rooting a Child's Whiteboard with Calculus. So, obviously we are not in class today, or rather I'm not in class today, but we're still going to examine some of those proofs that I wanted to look at. So we had two more derivative rules that we wanted to develop, and one of them was for a function that looks like this, f of x equals a to the power x. And the other one was for a function that looks like this, g of x equals log to some base to the power x. I'm just using a to represent just kind of any real number here. Now, you may recall that we've already done something similar to this. We've examined, well, what if we had a function like y equals e to the x? So what about the case where a is equal to e? In that particular case, you already know that the derivative is equal to e to the x. It's that unique result that we found the other day. And I think we also have a result for this as well too. Suppose we had a similar function, but just not with the base of a, but with the base of e. Then we had found that the derivative is 1 over x. And so we kind of expect our exponential function and our logarithmic function to have similar derivatives, because really they're similar functions, they just have a slightly different base. So I'm actually going to start by giving you the rules. So for a function like this, its derivative is a to the power x ln a. And the reason why that works if our base is e is because this would be e to the power x ln e. But of course, the ln of e is 1. And so it just ends up working out to being e to the power x. So that's going to be the property that we're looking to prove about that particular function. If we are differentiating, we can instantly turn that into that. And that's going to be our rule or our shortcut. So that's rule 1 that we're going to prove. Now, rule 2 is similar. Suppose g of x was logarithm of a, base a, x. Then we would have the derivative of g is equal to 1 over x ln a. And again, I'll just verify that this works if our base isn't a, it's actually e, like it is in this case. Well, because this is a base of e, then this derivative should be 1 over x ln e. But of course, as we saw above, ln e just happens to be 1. And so for both of these particular cases, we run into the situation where this ln e and the ln e that occurred up here are just what happens when we choose the better base. And so these all just come from that change of base thing. And we're going to see the change of base formula in both of these identities. And so this is going to be our rule 2 that we're looking to prove. And we'll go ahead and prove rule 2. I'm about to get interrupted by my toddler. So we'll see if I can do this with a toddler running around. Hi, Lark. Go around the other way. You're going to come in this way. Can you sit with Daddy? And we'll do a proof.
Just stop me.
Yeah, let's do a proof. Sit with Daddy and we'll do a calculus proof. Say hi to everybody, Lark. Can you say hi?
Hi.
Okay. So, if our function is f of x equals a to the power x, and we're looking for its derivative, we're going to start with the limit as h approaches 0 of f of x plus h minus f of x. This is all over h. So Lark, that's called first principles, okay? That's first principles. It's very important to know. You can play with the duck maybe. How about you play with the duck? Okay. Now we'll substitute into our function. So our function is a to the power x, so this is going to be a to the power x plus h minus a to the power x all over h. Yeah, I know. And then we're going to use common factoring to remove an a to the power x. So I'm still, the limit is h approaches 0, but I'll common factor out a to the power x now, leaving me with a to the power h minus 1. This is all over h. Now we've got a couple of things that are happening here. This a to the power x is constant, so I'm able to remove it and bring it to the front. So this will be 1 over, sorry, not 1 over, I apologize. This will be a to the power x times the limit as h approaches 0 of a to the h minus 1 over h. And this is still indeterminate because a to the 0 is 1, 1 minus 1 is 0. Now, we're going to have to do a quick little substitution here. Mark, can you go play with the bear so that I can do a substitution? Thank you. So, the substitution that we're going to do is we're going to replace a with something. So off to the side here, move the duck out of the way. We're going to let a equal e to the b. And so this means that b is equal to the ln of a. The reason why we're doing this is we're looking to use the construction of e. Remember, we defined it as the limit as h approaches 0 of 1 plus h. I'll show the substitution in a moment. I think we're under the clock here with Lark. We'll see how that works. So this is the limit as h approaches 0 of e to the bh minus 1 over h. Now we're
Daddy's.
Oh, that's Daddy's phone. You're right. Daddy's still recording a video. Yeah, I know that's nice you're saying cheese. Can I keep recording the video? Just gonna double check that we're still doing good. I think we're still doing okay. Do I have enough room? I think we can see everything still. Hope so. So recall that e is equal to the limit as h approaches 0 of 1 plus h to the power 1 over h. So we're going to replace this with e. So this is a to the power x, limit as h approaches 0, and then we're replacing e. So this is 1 plus h to the 1 over h, and that was all raised to the power bh. So we'll raise it to the power bh minus 1. This is all over h. Now, raising to a power of 1 over h and a power of h, those cancel because when we multiply, they turn into 1. So we're really going to be left with this expression, but I'm going to erase a little bit up here. So I'm going to go back up to the top, and I'll erase first principles, and leave my last line. But we'll show how this substitution works. So we're back up here. Watch out, Lark. If a to the x, the limit as h approaches 0. Now this is 1 plus h to the power b now, because those cancel, minus 1. Oh great, you let the dog in. Lark, can you bring Rowan to his place? Welcome to comedy, folks. Okay, Rowan, out. Oh, sit. 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 I know this is boring. Thank you, Lark. Tell him to stay. Now, this is still not indeterminate form. So, sorry. This is still I better have a sip of coffee. This is still an indeterminate form because if we substitute in 0, we have 1 minus 1, 0 over h. We're going to expand this using the binomial theorem. So this is going to be 1 plus bh plus, and we'll have a bunch of coefficients, but just the important part to remember is the exponent on h is increasing. And so there's going to be a bunch of terms with a bunch of different coefficients. And these are all based off of b choose, this is b choose 1, this is b choose 2. And they would just continue up and up and up. But your last term you're going to have is h to the power b, and then minus 1. All over h. Oh, I forgot my limit notation. See what happens when I get distracted by kids and dogs. And so we've expanded this now using the binomial expansion. I want you to notice that every single term here contains an h, except for this one. But that plus 1 and that minus 1 are going to cancel out. So they're gone. And because every single term contains an h, I can factor out an h from each term. Now this one will still contain one more h, and every single other term in here will still contain other h's as well. So in fact, all of these terms are going to go to 0 when we divide, when we substitute in. So we'll cancel an h from each term, and in the numerator and denominator, yes, sweet. And then all of those terms containing h would cancel. And so really we're just left with ax b. Because that b is the only thing that remains when we get rid of the determinant form.
Oh, no.
Now, we can't call no Lark. Now remember, b is equal to ln of e. Sorry, ln of a. So this works out to be a to the power x. You're right, it is Daddy's coffee. Thank you. Thank you, Lark. So b was equal to ln of a. So we're left with a to the power x equals ln a. And that was the rule that we were looking to prove in the first place. We were looking to show that the derivative was a to the power x ln a. So it's kind of devolved into chaos here. I'm still going to post this video because I think we were actually able to get through the development. I feel like this last step might be a little bit confusing, but it's very similar to when we proved the power rule. So just go back in your notes and review the proof of the power rule to see how everything else there canceled, because there was at least one more h in there. So when we evaluated the limit, all of those terms went to 0. Take good care, and I will do the note for logarithm probably before lunchtime, and I'll be putting out a podcast for optimization shortly as well too. Say bye, Lark. Say bye, Rowan. Say bye, Charlie.